Hello, in this video we're going to go over the idea of norm and what are the properties, and then we'll talk about a couple of examples. Okay, so first, what is norm and why do we need that? If you recall, in the previous video we talked about angles between two vectors. So if you have two vectors, we can define angle between two vectors, and that allows us to understand the geometry of Rn or different geometries of Rn. Now there is no reason for us to define the length of a vector using the definition of angle. We could also just define the length of a vector directly by using properties of length rather than defining the angle between two vectors and then using that to define the length of a vector. So there are some certain properties that we expect from length of a vector. The first one is length would have to be a positive number unless the vector is 0. The second property is, if I take a triangle, we know the triangle inequality. Two sides add up to a number that is more than the third side unless the triangle collapses into a segment, in which case we have equality. So we could have a plus b greater than or equal to c for every 3 length ABC of a triangle. If it is a degenerate triangle, in other words, if it's a segment, then it could have equality. And the third one is, if I have a vector v and I scale that with a factor of c, so length of c times v would have to be absolute value of c times length of v. So if you double a vector, you would expect its length to also be doubled. These three properties are called norm properties. So formally speaking, a norm on Rn is a function that assigns to any vector v in Rn a non-negative real number norm of v that satisfies all of the following. So norm of v is positive for every non-zero v. That property is called positivity. Then we have triangle inequality. So if I have a vector v and I have a vector w, then this would be vector v plus w. So this is v, this is w. Norm of the third side is less than or equal to the sum of the norms of the two sides of a triangle. And if I take norm of cv, that would be absolute value of c times norm of v for every vector v and every scalar c. Okay, so these are the three expected properties of a norm. Now let's look at an example. This is a very important example, since it in fact shows us that length that we defined before is in fact a norm. So here is the property. If you have an inner product and you define length of v as square root of product of v with itself, inner product of v with itself, it is a norm. Okay, so first I will have to show positivity. So suppose v is non-zero. So what do we know by positivity of inner products? If you take the inner product of v with itself, that would be positive, which means if I take the square root of that, that would also be positive. In other words, it's not 0, which means this definition that I have, which we want to show its norm, is in fact positive. Okay, so that's the first condition. The second condition is the triangle inequality. So we need to show, if we take norm of v plus w, so norm of v plus w is inner product of v plus w and itself, and we'll have to take the square root of that, is less than or equal to norm of v, which is square root of inner product of v with itself, plus norm of w. So notice that I'm saying we need to show this one. I'm not saying that this is true. I'm just saying that we need to show this one. Now, given that both sides are positive, this is equivalent. And again, this is very important that notice that I can go backwards in every one of these steps that I'm taking. The forward direction is actually not very helpful in our proof. The backward direction is what really matters. So I can square both sides, and I can also take the square root of both sides because both sides are positive. This is equivalent to saying v plus w, inner product with v plus w, is less than or equal to inner product of v and v plus inner product of w and w plus twice square root of inner product of v and v times inner product of v, w, and w. Okay, again, I really need to go backwards. This is the proof. And I can't go backwards because I can just take the square root of both sides. Now, this is equivalent to, I'm going to use linearity of inner product. That would be v inner product with v. Again, this is all equivalent. Plus v inner product with w. I'm simplifying this expression here. Plus inner product of w and v plus inner product of w and w. That is less than or equal to inner product of v and v plus inner product of w and w plus twice square root of inner product of v and v. I'm not changing anything on the right hand side of the inequality. Okay, so now again I'm going to write down something that is equivalent to this one. I emphasize that I cannot emphasize this enough because this is a very common mistake. I am not assuming the conclusion. I'm making sure that I write down things that can be reversed. So canceling this can be reversed because you just add those two quantities to both sides. So this is the same as twice inner product of v and w is less than or equal to 2 times square root of v, inner product of v and v, and then w and w. Now notice what happens here. This is equivalent to inner product of v and w is less than or equal to length of v times length of w. So if this is true, then the previous one would be true, which means the previous one would be true, which means the previous one would be true, which means the original inequality would be true. So this would be our proof. Now, why is this last one true? This holds by the Cauchy-Schwarz inequality. So notice that Cauchy-Schwarz inequality, just to remind you, Cauchy-Schwarz inequality was inner product of v and w in absolute value is less than or equal to length of v times length of w. This was the Cauchy-Schwarz inequality. And of course, we know that absolute value is, of course, greater than or equal to the a number itself. So therefore, if you combine these two, you get the inequality that you want. So this proves the triangle inequality. Now we will have to show the last property of inner product, which is homogeneity. Okay, so we'll evaluate the norm of CV by that definition. This is the square root of inner product of CV and itself. By linearity, we can take the c out, so it would be c squared inner product of v and itself. And I can take the c out, so square root of c squared is absolute value of c, and then v inner product with v, and then you take the square root. So what does that mean? It means it's equal to absolute value of c times the length of v. So this length satisfies all three properties of norm. Therefore, this function, square root of v defines a norm on Rn. Okay, and that's the end of the proof. So this is interesting. So we are actually able to prove the triangular inequality using the Cauchy-Schwarz inequality. In fact, this idea of norm that we defined is an extension of the previous idea in terms of defining the length. Okay, let's do one last example, and then in the next video we're going to talk about a new topic. Okay, so the following are examples of norms on Rn. The first one is the Euclidean norm. So why is that norm? Well, the reason is, if you look at the first one, if you think about that, that is just the definition of norm length using dot product. So the norm of x1 through xn, it is just square root of the inner product of x1 through xn and itself. So by the previous example, or I guess the theorem, by the previous theorem, we're done. This defines a norm. Okay, so that's A. Now let's look at B. This is in fact also going to define a norm. Maximum of absolute value of x1 all the way to absolute value of xn. So why does that define a norm? So we will have to show those properties. So positivity. So let's look at positivity. Suppose x1 through xn is not 0. So that means xj isn't 0 for some j. Now, if you look at the maximum that they gave us, maximum of absolute value of x1 all the way to absolute value of xn, that is at least absolute value of xj. But absolute value of xj is positive because xj is not 0. So that means it does satisfy positivity. Okay, so next one is triangle inequality. Take two vectors. So suppose x1 through xn and y1 through yn are in Rn. Now, let's take the norm of x1 plus y1. This is the sum of the two vectors, xn plus yn. This norm that they gave us is the maximum of the absolute values, x1 plus y1 comma xn plus yn. Now, maximum would be one of them. So let's assume this is absolute value of xj plus yj. So let's make that assumption. It's just one of those. Let's assume it is this one. Now, by the previous example, this is going to be less than or equal to absolute value of xj plus absolute value of yj. Why is that true? This is because square root of x squared, which is absolute value of x, is a norm for R. So previous example told us square root of x1 squared all the way to xn squared, so that sum. Let me move up here. This one. If you set n equals 1, you get norm of x1 equals absolute value of x1. This is a norm, which means it satisfies the triangle inequality. So it means absolute value of xj plus yj is less than or equal to absolute value of xj plus absolute value of yj. But this is less than or equal to, since it's one of those xj's, it would be less than or equal to the maximum. So maximum of absolute value of x1 all the way to absolute value of xn. And of course, the same holds for yj. That's less than or equal to maximum of y1 all the way to absolute value of yn. But that's exactly the norm that they gave us. Norm of x1 through xn plus norm of y1 through yn. So I haven't really shown this is a norm yet, but I call it a norm just for convenience. So that shows the triangle inequality. Finally, we'll have to show the homogeneity. Okay, so I'll have to look at norm of c times x1 through xn. This is equal to maximum of absolute value of cx1 all the way to absolute value of cxn. Because if you look at the vector right here, this is just cx1 all the way to cxn. So what's the largest of those? The largest would be absolute value of c times maximum of x1 through xj. And the reason is, let me explain that. x1 through xn, which is absolute value of c and then norm of x1 through xn. Okay, so here is the reason. So the reason for this one, if c is equal to 0, so basically what it says is this. I don't even need to take cases. So if xj is greater than or equal to xi, then absolute value of cxj would also be greater than or equal to absolute value of cxi. So if the largest among all the xj's among x1 through xn is xj, absolute value of xj, then the largest among these would also be absolute value of cxj. So that's why we have this equality. And that gives us another norm which is in fact in nature different from any of the norms that you obtain from inner products. And that one is not quite obvious, but it is possible to prove that this norm in fact does not come from any inner product. Okay, so that brings me to the end of this video. So I will see you in the next video.